Right, what we'll do in this final section on sequential Erlang is to talk about runtime errors, different kinds of errors that can be created, and ways in which those errors can be handled. What we'll do is run through a sequence of examples that show the sorts of errors that you can get. A general class of errors we get are what are called match errors. There is pattern matching in Erlang that decides which of a number of function clauses is executed, or a case expression, and so on. And it's possible to get an exception for no function clause matching. What we've got here is factorial. First clause applies to positive numbers, the second to 0. So if we apply to a negative number, no clause applies, and so what we get is an exception error saying no function clause matching math factorial -1. Here we've got a function with a case switch, which switches over the value of n being -1 or 1. So if we apply the function to 0, we get an exception due to that pattern match failing. There is no case clause which matches 0. So we're getting accurate errors for these functions. In a similar case, if we have a case, an if, where we switch on whether n is less than 0 or n is greater than 0, if we apply the function to the argument 0, we're going to get an exception from an if expression. And again, what you see here is the error message we get back in the shell is precisely describing that property. Now finally, pattern matching is a very general process, so it's possible, as you see in the example here, to bind a 3-tuple to the variable tuple, and then to try and match that variable here to a 4-tuple. And what we have got here is an error you see quite often. It's a no match of right-hand side value, and that generally says that a pattern match has failed. That can happen because the shape of the pattern you're trying to match doesn't match the expression on the right-hand side. It can happen because you're rebinding a variable, because remember, you can have bound variables in patterns, unlike other languages with pattern matching. So if you write x equals 2, full stop, and then you match on x equals 3, the error that you'll get is a no match of right-hand side value. This bad match covers a number of programming errors. Other things we can get is if you have a function which works over lists, for example, and you apply it to an atom, you'll get what's called a bad arg, a bad argument exception. And you see that for length. Length expects a list, it's been given an atom. It's possible to call a function that isn't defined, and that will give you a message saying precisely that that function isn't defined. It's possible to try to add an atom to a number, and what you get there is a bad argument in an arithmetic expression. So those are the sorts of errors that can get created in evaluating an Erlang expression. The question is, what can we do about that? How can we handle those expressions? What we're going to cover here is the original Erlang exception handling mechanism called catch. A lot of legacy Erlang code will use this exception handling mechanism. More recent code may well use the try catch mechanism, which I'll show you an example of at the end of this discussion. But what we have here is catch. Catch is applied to an expression, and what it will do is, as that expression is evaluated, it will trap any exits caused by runtime errors. And what will happen is that we will return the tuple, which consists of the exit atom together with a reason for the runtime error that has occurred. So that's the catch turns what would be an exception in the shell, and which cause the shell to die. What we see instead is that a concrete value is returned as a result of that catch. Let's take a look at an example. The reason we're using self here, it's a BIF. It tells you the identity of the current process. And it returns a thing called process ID. This is stuff that we'll talk about in the next section. The reason we're looking at it here is it's showing us when in fact the process that's running the shell has died and has been relaunched. But let's just, in command 1, you can see that we're getting the ID of the shell is 28. Now, if we call the function list to integer on a list ONE, that will fail, because what is expected here is that the string which makes up the list is a digital string, a string of digits. So this fails. If we call catch, what we get is this long tuple returned, which begins with exit, and then you see a tuple which describes the exit, the error, in a lot of detail. You can see it's a bad arg is the tag for the tuple, and then what you have effectively is a stack trace of calls that have led to that bad arg error. So we get a lot of diagnostic information back from that. And you can see that calling in command 3, calling self, we've still got the same process running. If now you call list to integer, make the same function call, but in the shell, what happens is that an exception has been called. We get the error message saying bad argument, as we heard earlier. But what you see is that actually killed the shell process, and it's been relaunched as a different PID, 33. So the caught exception returned an ordinary value. The uncaught exception killed was handled in the shell and relaunched the shell. So there you see the essential difference between a caught exception and an uncaught. Here's another example of a bad arith error, dividing 1 by 0. You get a bad arith. Just a little piece of syntax, which is frustrating. You need, if you're going to bind a caught value, you need to bracket the catch as you see it there. So if you write x equals catch 1 divided by 0, you get a syntax error. What you need to do is bracket that whole call to catch. And you can see in command 2, the one that's failed, you get the same effect as we got just calling that expression. Now, the errors that we've been catching so far are errors caused by the evaluator, bad match, bad arith, or whatever. It's possible to raise your own errors using a throw primitive, and that effectively gives a non-local exit to a function call and execution flow. It jumps to the first catch in the execution stack. A typical example for this is perhaps you're deeply within a tree representing a piece of syntax or an XML tree, and you encounter an error. You don't particularly want to unwind all the stages that you entered. You just want to say, oh, I failed, just give up. So that would be a typical example of using, you'd throw an exception at that point and expect at the next level up you would catch that exception and move on perhaps to processing the next tree. I think we can see an example here. We've got an add function which tests the value of y, tests the value of x, and then returns the sum. And what test does is when x is an integer, it returns OK, otherwise it throws an exception. And if we call the function add with an integer and an atom, we get, and catch the exception, we get a non-integer coming out of that. If we catch, if we throw the exception bye-bye and catch it, we get bye-bye. If we catch a call where the exception isn't raised, we simply get the ordinary value back. And if we throw an exception without catching it, we've got an exception which has to be handled by the shell. So I think there you see the interaction of catch and throw, and it can be used as part of ordinary arithmetic processing. You can see if we go back to line 1, what we've got as a result there is an error tuple, and at some point what we'd have to do is deal with that error tuple and perhaps convert it into a number that could be returned to whoever is calling this version of add. Before we conclude, what I want to do is talk about try-catch. So let me show you an example on the board. What we see here, we have an expression of this form. We have an expression which we evaluate, and according to its value, if it matches pattern 1, we'll perform body 1. If it matches pattern 2, we'll perform body 2, and so on. But we can also say, if it raises an exception of a particular sort, we will perform this recovery code. So we might have pattern 1 there, pattern 2 there, and so on. So this gives us a structured way of dealing with code that might raise an exception. If there isn't an exception raised by that, we deal with the value in this way. If there is an exception raised, we deal with it in this way. And what's nice about the code here is we can distinguish between different kinds of exceptions. We can distinguish between sort of erroneous exceptions like bad arg, exceptions which are thrown by programmatically, and an exit message, which we'll find out about more about later on in the course. So here we've got this rather more structured way of dealing with things. So we can be sure we can distinguish exceptions of different kinds in this way, and we also get we combine the ordinary handling and the exception handling into a single construct, which is more flexible and more integrated than the catch on its own. Okay, well that concludes what I wanted to talk about with exception handling. In fact, that concludes the overview of sequential Erlang. What we've talked about here is, first of all, built-in functions and libraries. So the infrastructure, if you like, that is provided by the system, the existing system, and the manual pages and documentation that describe those. And we've also talked about the general control structures for these sequential aspects of Erlang, about how you can perform different alternatives according to case, which is pattern matching based, or if then else. We've got guards and a particular restricted syntax that you can use within guards. And we've got recursion, which gives looping, which gives iteration. It's a general control construct for which gets used throughout Erlang programs. And also we talked about some of the runtime errors that can occur and ways that those can be handled using catch and throw. And just recently, in this last example, how you can use try-catch to combine normal and exceptional behavior in a single construct.